Hello students, welcome to Getronics for you. In this video, we are going to discuss about the bond model of semiconductor. To understand this bond model of semiconductor, you must watch the previous video. If you haven't watched that, please go to the previous videos, watch those videos, then come to this video. Let's start the bond model of semiconductor. To explain the bond model of semiconductor, we will take an intrinsic semiconductor. Let us assume an intrinsic semiconductor. So what does this intrinsic semiconductor means? Means it is a pure semiconductor material. Pure means it is nearly 100% pure. Pure means that there will be only the corresponding semiconductor atom present inside material. Consider our semiconductor materials, that is, we will explain the bond model of the semiconductor taking that semiconductor material is a silicon material. Now, this bond model is a qualitative aspect of explaining what is happening inside the semiconductor. And for this case, we have assumed that the semiconductor material is a silicon material. Later, we will translate them into the equation. And the qualitative means a rough will not get the exact picture, but will give a rough picture that is what is happening inside the semiconductor. That is, we can say that bond model will not give the accurate calculation, but we can have a feeling what is happening inside the semiconductor. So in summary, we can say that the bond model of semiconductor will not give you the accurate calculation about the phenomenon that's taking place inside the semiconductor, but we can get a feeling or we can get a rough idea what is happening inside the semiconductor. So from the bond model, we can get some information about the semiconductors. So let us see what are the information that we can gather from the bond model of the semiconductors. So from the bond model of the semiconductor, we can get these 5 information. These are the 5 information that we can get from the bond model. The first one is why there are electrons and holes inside the semiconductor. We can get the reason why there are electron and holes inside the semiconductor. This is the first information that we can get from the bond model. The second information that we can get is why electrons are negatively charged and holes are positively charged. This information can also be found from the bond model. And the third information that how the carriers will carry current. That means these electrons and holes, how they are carrying current. The fourth information that we can get that what happens to the semiconductor when the temperature will be increased. The fifth one that we can get a rough idea about the concentration of electrons and holes. We will not get the accurate value of electrons and holes, but we can get a rough idea about the electrons and holes. So these are the information that we can get from the bond model. Let us go into the energy bond model of semiconductor. To model the semiconductor, using energy bond model, we have to follow some steps. So there are several steps we have to go through to model the semiconductor using the energy bond model. The first step is that we have to understand about the crystal structure of the semiconductor, and we have assumed that our semiconductor material is a silicon material. We have to understand the crystal structure of silicon material. Next step, we have to see what will happen in the silicon crystal when the temperature will be 0 Kelvin. And in the step 3, we will see the silicon crystal for temperature greater than 0 Kelvin. So let us first go to the step 1. So in the step 1, we are going to look into the crystal structure of silicon. So as the name depicts, that silicon is a crystal material. Since silicon is a crystal in structure, so there must be regular arrangement of atoms. So what does this regular arrangement of atom means? It means that there will be a small block, and that small block will be repeated periodically to get the whole crystal structure, and the small block will be called as the unit cell. So we can say that it involves the repetition. So we can say that it involves the repetition of unit cells or unit cube. For this case, to understand the crystal structure, we need to know the unit cell structure or unit cube structure of silicon. So let us see how the unit cell of a silicon material looks like. So this is the unit cell structure of a silicon material, and this unit cell will be repeated periodically to get the whole structure. So in the unit cell, actually it is a simple cube. At the every corner of the cube there will be atom. So we can say there will be 8 corner atoms in the unit cell, and there are 6 faces of this cube, and in each face there will be a atom in the middle of the face. So there will be 6 face. So there will be one atom at each of the 6 faces. So one atom at each of the 6 faces. So there will be 6 atoms. Now, along with these atoms, there will be another 4 atoms like this. Let us name this corner as it is the A corner, and this corner is the B corner, and this is the C corner, and this is the D corner. So we have named these corners. Now, from this A corner in this direction, by an amount of A by 4 distance, and A is the total length of the cube, or it is the lattice constant. So if I move A by 4 distance from this A point, and from this point if I move A by 4 distance in this direction, so this is also A by 4, and from this point if I move in the upward direction by A by 4 point, then we will get a position here, and at this position there will be another atom. So this atom is situated at, if we move a by 4 in this direction, then a by 4 in this direction, then a by 4 in this direction, then we will get this atom. Similarly, if we move a by 4 from the B corner in this direction, so this is a by 4 distance, then we will move a by 4 in this direction, so this is also a by 4, and from this point if I move in the upward direction by a by 4 distance, then at this position we will get another atom. These are the two atoms that we can get. Similarly, if I move a by 4 distance in this direction and a by 4 distance in this direction, this is also a by 4, and if I move downwards in this direction by a by 4 distance, then at this point we will get another one atom. Similarly, we will get another one atom if we move in this fashion, and we will get one atom at this point. So you can see there are four atoms. If the two atoms are in the AB diagonal, then the other two atoms will be in the perpendicular diagonal always. So this is the total structure of the unit cell of the silicon. So we can write here that four corner atoms, out of which two atoms are at AB diagonal and two atoms are at CD diagonal. Always these two diagonals will be perpendicular to each other. So this is the total structure of the unit cell of silicon, and this A is the lattice constant. So this is the final structure of the unit cells of the silicon material. Now if we look at the structure closely, then we can see that every atom or each atom is bonded to the four neighboring atoms. Let us take at this atom. This atom has one atom here, another atom here, another atom here, and another atom here. So there are four neighboring atoms for each atom. So we can write that each atom is bonded to four neighboring atoms. That's why silicon has a valency of 4 also. Valency means how many neighboring atoms are there also. You can also say that valency means how many electrons are there in the outer orbit, but valency also signifies how many neighboring atoms are there for each atom. So if we look at the structure of this silicon unit cell, we can realize that it is very difficult to work with this 3D structure or 3D arrangement. We have to make it simpler. So to make it simpler, we only take two important aspects from the 3D arrangement. So what are these aspects? So the first aspect that we will take from the 3D arrangement is a regular arrangement of the atoms. That is, there will be a regular arrangement of atoms inside the silicon crystal structure. The second aspect that we will take is that each atom will be bonded with four neighboring atoms. With these two aspects, we can draw a equivalent 2D structure. Using these two aspects, if we draw the equivalent 2D structure, it will look like this. This is the 2D structure that we can draw using those two important aspects that we have got from the 3D structure. Here you can see these are the silicon atoms, and this is the bonds. This is the bonds in between the two atoms, And you can see that every atom is bonded with 4 neighboring atoms. Every atoms. So this is the 2D structure or 2D representation that we can draw from that 3D representation. So we can write here 2D representation of silicon. Now let us see some practical values or practical data for silicon, and those are: for silicon material the atomic number is 14, valence electrons is 4, atomic concentration is 5 into 10 to the power 22 atoms per centimeter cube, and lattice constant, that is A, is equals to 5.43 angstrom, and the bond energy is 1.12 electron volt. These are the practical data for a silicon material. This bond energy means how much amount of energy is needed to break these bonds. So we can write energy needed to break the bonds between two silicon atoms. And we also know the bond of silicon is of covalent nature. So these are covalent bond. This is all about the crystal structure of silicon. And in this crystal structure of silicon, step 1, we have found a 2D representation of silicon from the 3D representation of silicon, and we will use this 2D representation of silicon for explaining the phenomena that will take place inside the material for higher temperatures. Now let us go to the step 2, that is, what will happen inside the silicon material at T equals to 0K. To explain this, let us consider the 2D representation of silicon, which looks like this. In this diagram, you can see these are the silicon atoms and this is the covalent bond. Now, since the temperature is at 0 Kelvin, so there is no thermal excitation on the silicon material. Since there is no thermal excitation, so the silicon atoms will not vibrate. That is, no agitation of the atoms will take place. Since there is no agitation of atoms inside the semiconductor material at T equals to 0K, so there will be no breaking of bonds inside the semiconductor. Since there is no breaking of bonds inside the semiconductor, so we can say no free electrons will be generated. Since there is no free electrons inside the semiconductor at T equals to 0K, so we can say that silicon material will behave as an insulator at T equals to 0K, because there is no free electron inside the semiconductor at T equals to 0K, so no current can flow inside the semiconductor at T equals to 0K. Hence, it will behave as an insulator. So far, we have seen that the silicon crystal behaves as an insulator at T equals to 0K. So we can write silicon crystal behaves as insulator at T equals to 0K, because at T equals to 0K there will be no thermal energy that will create any electrons, that is free electrons, inside the semiconductor, because there is no bond breaking inside the semiconductor. And if the energy bond do not break, then there will be no free electrons. That's why silicon behaves as an insulator at T equals to 0 K. Now what we will do, we will increase the temperature. So in the case 2, we will increase the temperature such that temperature is greater than 0 K. Now let us see what will happen if we make the temperature T greater than 0 K. So since the temperature is greater than 0 K, that means a finite value of temperature, then the atoms inside the silicon crystals will start vibrating. Since the atoms start vibrating, so there will be atomic displacement takes place. Due to this atomic displacement, we know that from wave particle duality, elastic waves will be generated. And according to the wave particle duality, we can say that elastic waves is nothing but the phonons or stream of phonons will be generated inside the silicon. In this way, if we make the temperature greater than 0 K, then a stream of phonon particles will be generated inside the silicon crystal. So we can write, if the temperature capital T is greater than 0 K, then phonon particles will be generated inside the silicon crystal. After phonons are created, due to the increment of temperature, photons will also be created. So let us see how the photon particles will be created after phonon particles has been created due to the increment of temperature. So now we want to see right now that after phonons are created, photon particles will also be created, and we want to see how. To understand how photon will be created, let us consider an atom of silicon like this. So this is an atom of silicon. Let us consider. So you can see this is the nucleus part of the atom, which is just in the middle of the atom. So this is the positive nucleus part. So we can say this is the positive nucleus of the atom, and the shaded region is the electron cloud, which will be negatively charged. So let's first take T equals to 0 K. So when the temperature will be at 0 Kelvin, we know that there will be no external thermal energy. And from this diagram, we can say that this positive nucleus will have a mass center, and this negative nucleus will also have a mass center. Mass center means a point where the total mass is concentrated. So nucleus has some mass, and we should have some mass center. Similarly, for the electron cloud, we will have a mass center. So now let us consider that the temperature capital T is at 0 K. So if the temperature is at 0 K, then we can say that the atom will not have any vibration. So we can say that the mass center of nucleus and the mass center of electron cloud will coincide with each other, because the atoms are static now. But during temperature is greater than 0 K, atom starts vibrating, And when atom starts vibrating, that means this atom will start vibrating in this fashion. It will vibrate in this direction, up down, or in this fashion. So when it will vibrate, the mass center of the nucleus, this one, and the mass center of the electron cloud will be displaced from each other, because when atom starts vibrating, then we can say that since the nucleus part, we know that the nucleus part has heavy mass and the electron part has a very lower mass. So when the atom starts vibrating, then the mass center of nucleus and the mass center of electron will be displaced from each other, and the picture of the atom will look like this. In the picture you can see that this is the mass center of the electron cloud, and here in this point this is the mass center of न्यूक्लियस। जब ये वाले एटम वाइब्रेट करना चालू होगा तब क्या होगा, न्यूक्लियस के मास ज्यादा होते हैं और इलेक्ट्रॉन क्लाउड के मास कम होते हैं, तो दोनों का वाइब्रेशन फ्रीक्वेंसी अलग अलग होंगे। अगर वाइब्रेशन फ्रीक्वेंसी अलग होता है तो न्यूक्लियस का मास सेंटर कोई भी एक इंस्टेंट पे इलेक्ट्रॉन क्लाउड का मास सेंटर से डिस्प्लेस्ड हो जाएंगे। So there will be a displacement in between the mass center of the electron and the mass center of the nucleus. So we can see that this mass center is negatively charged, but this mass center is positively charged. So a positive and negative charge center has been displaced from each other. So यहाँ पे हम लोग देख रहे हैं कि नेगेटिव चार्ज सेंटर एंड पॉजिटिव चार्ज सेंटर दोनों एक दूसरे से डिस्प्लेस हो गया है। अगर डिस्प्लेस हो जाते हैं, so we can say that a vibrating atom will create a oscillatory dipole. So we can draw like this the negative charge center here and the positive charge center for the nucleus, and it is vibrating. Hence we can say that vibrating atom is an oscillatory dipole, and we know that oscillatory dipole will radiate electromagnetic wave. And according to the wave particle duality, we can think electromagnetic wave as photon particles. So every vibrating atoms is the source of electromagnetic wave or photon. So in this way, photon particles are generated inside the semiconductor when the temperature is raised above 0 Kelvin. So right now we can say that at T, or temperature greater than 0 K, there will be two particles generated inside silicon crystal. The first particle that has been created is the phonons, and the second particle is the photons. And these phonons and photons will now interact with each other, and if after interaction the total energy is greater than the bond energy of the silicon, then it is possible that the bond of the silicon will be broken. So we can write, during the interaction, if the total energy of this particle is greater than the bond energy of silicon, then it is possible to break the silicon bond. And we know that the bond energy of silicon is equals to 1.1 electron volt. If the total energy is greater than this 1.1 electron volt, then the bond in between the silicon atom will be broken. And we know that in a bond there are two electrons and if the bond breaks, electron will be set free, and this free electron can move freely inside the crystal. In the place of free electrons, there is a scarcity of negative charge that will act as a positive charge called holes. So far, we have seen that if the temperature of the semiconductor, that is capital T, is increased beyond the 0 Kelvin, then two types of particle has been produced. First one is the phonon particle and the second one is the photon particle. And when this phonon and photon particle will interact with each other, and if the total energy is greater than the bond energy of the silicon, then the bonds of the silicon will be broken. So if the total energy E total is greater than 1.1 electron volt, which is the bond energy of the silicon, then bond of silicon breaks. As we know that in a single bond of silicon there are two electrons. So when the bond breaks, electrons will be set free. So to understand this scenario, let us take the 2D representation of the silicon crystal. This is the 2D representation of the silicon crystal, and these are the silicon atoms. Now, if the total energy is greater than the 1.1 electron volt, let us assume that this bond breaks. And if this bond breaks, then the electrons that are inside this bond, that is the two electrons, one of the electrons will be free, so a free electron will be produced. And in the place of free electron, there is a scarcity of negative charges which will act as a positive charge. And this positive charge, or the vacancy of negative charge or vacancy of electron, is called the hole. So we can say that this one is the free electron and this one is the hole. In this way, phonon and photon interaction can produce a free electron and a hole by breaking the bond of silicon. It happens only when the total energy of interaction of phonon and photon will be greater than the silicon bond energy, that is 1.1 electron volt. In a summary, we can say when T is greater than 0 K, within the semiconductor there are four types of particles. The first one will be the phonons, that is the atomic displacement or elastic wave, and next, due to the vibration of the atoms, photon particles will be created, and due to the interaction of phonon and photon and breaking of bonds, free electrons will be created, and in the place of free electron, holes will be created. So in this way, inside the semiconductor at temperature greater than the 0 Kelvin, four types of particle can be produced. And these free electrons that has been produced are not attached with a single atom. It can move about anywhere inside the crystal but cannot go outside the crystal. Not a single atom can say that this free electron is mine, and with every free electron inside this semiconductor, a hole will be created, and the process by which a free electron and a hole is created simultaneously is called the electron hole pair generation. So we can write that the process by which free electron and a hole is created is called electron hole pair generation. In short, it is called EHP generation. And since the semiconductor is in equilibrium condition, the concentration of electron, holes, and photon and phonons must be maintained constant because the semiconductor is in equilibrium. And we know that equilibrium means every process there should be a reverse process at the same rate, then only equilibrium can be maintained. That means for EHP generation there must be a reverse process taking place inside the semiconductor, which will make the constant concentration of electron, holes, photons and phonons. And the reverse process of this electron hole pair generation is EHP recombination. And what is this EHP recombination? The free electron which has been created due to the interaction of phonon and photons has some energy due to thermal agitation, because they has been created due to thermal agitation. And during the movement of the free electron, as we know that the free electron can move freely inside the crystal, the free electron can encounter with any one of the holes inside the semiconductor and reside on the hole. So a electron and hole has been recombined, and that is called electron hole pair recombination. This is all about the bond theory of semiconductor. In this bond theory, we have seen that how the four types of particles has been produced inside the semiconductors, and we have also discussed about the electron hole pair generation and electron hole pair recombination. And this concept of energy bond modeling of semiconductors is very important with respect to the interview purpose in the PSU cases, and it will help to understand the semiconductor physics in the upcoming lectures. Hopefully you have enjoyed this video, and please do subscribe the Get Electronics for you. Please like and share the video as much as possible so that more number of students can be benefited from this video. So enjoy your GATE preparation and keep watching Getronics for you. Thank you.